Okay, the recording has started.
Alrighty, so just want to go through here. So we have me, Zach Phillips, Jim Jarvis, ESRA Safety. Do we have mentor flyer record with us on this, or?
Yeah, Andre is here, but I mean, he's just listening since he
Okay.
has he's at the office and he has something to deal with.
Okay.
Yeah, I'm here. I'm not too far.
Okay. Awesome. So looks like I don't see a presentation, so we're just gonna go through the rocket then.
Yeah.
Okay. If we want to start from bottom of the booster and just work our way up through everything, that works for me. Is that fine with you, Jim?
Yeah, I like starting. I'm not sure why, it just makes more sense to me.
Starting what? Sorry, I think it had cut out.
I said, yeah, starting from the bottom is fine.
Okay. Yeah, so you guys
I
wanna?
see what the problem is. Okay. Fixed my problem here.
So we're gonna film a close-up from a phone. So at the very end, there's the retainer, which is an touch retainer. And it's connected to a SRA, the truss plate, that just slots itself at the bottom of the composite tube. There's 4 screws to hold it in from falling, but the truss upwards is from contact with the tube. There's one of the 4 screws that its use is also to connect a rail button. And yeah, that's pretty much it for the very end. Then we have a motor tube inside, so a cardboard motor tube that's held to some resin 3D printed centering ring that we see here. They also are used to slot the fins and connect them to the motor tube, and they hold them in place from the sides with like pretty sturdy tabs, and there's fillets with epoxy. The fins themselves are composite fins, so there's 2 composite carbon skins on each side, and at the middle is a foam core, so a divinacell core. The layup was made to prevent flutter, so there's 45-degree plies and 90-degree plies to have better force inflection and torsion. Then on the way up, there is a carbon fiber tube. All tubes are Schwab, so we all made them from resin infusion on an aluminum mandrel. They're all 142 millimeters of diameter in the inside. So yeah, motor tube goes through all the way here. It stops at some point, and the motor is just hanging. It's not really connected at the top since the truss is from the bottom. There's a centering ring here with a place for the rail button. We have a permanent coupler, a carbon coupler for the 2 parts. So this tube and this tube are permanently connected. We just need to, it won't show at the end because we have a finishing touch here to hide the junction. Next, we have a bulkhead here, which is the end of the motor part of the tube and the beginning of the parachute part. So we have a parachute bay from the bulkhead here all the way to the end of about here, the end of the coupler, where there's the avionics bulkhead. Inside this bay, there's 2 parachutes since it's a single bay. So there's the main parachute and the drogue parachute. They both go out at apogee, but the main parachute stays shut on the shock cord with some, well, we call them line cutters, but they act a bit like the Jolly Logic chute release, only that they are connected to the altimeters with a thick wire that goes along the shock cord. Then in this fiberglass tube, there's the avionics bay. So the booster avionics bay that will go is assembled right there. And at the top, there's the assembly for the interstage. So the top bulkhead of the avionics is screwed in the fiberglass tube with 4 M5 bolts, and there's a pressure, but not pressure, but the thrust goes inside the bulkhead and pushes through the sustainer motor casing. And it's aligned in place by a smaller carbon fiber tube that's right here. So we'll show a bit better on the other side when we go to the sustainer, but yeah, there's this tube that prevents the whole sustainer from bending, so it's in place here inside the other tube and centered with the bulkhead assembly and holds the sustainer in. I guess that's pretty much it for the booster part.
Let me ask a question about the recovery, the cable cutter method.
Yep.
Which cable cutters are you using? Are they your own or commercial?
Well, it's a. Show it. Well, it's based on a design from ALFCAT rocketry. We tested them for the first time last year, a flight test at the Launch Canada competition. So yeah, it's based on the ALFCAT rocketry design, but it's parts from McMaster, and it's built by ourselves.
Okay, so it's the half cat version.
Yeah, so that's the idea. It's a tube with a pin, some black powder. The igniter goes one way with a screw with a hole. The other side is closed. And yeah, there's a tie wrap that goes through both line cutters, so either one can open the parachute. And yeah, that's it, I think.
Okay, and so you have when the apogee event occurs, you put out a drogue chute on harness.
Yeah.
And also then the main then is bundled outside of the airframe.
Yeah, it's bundled with a D-tie wrap that goes through both line cutters, and it's attached and it goes around the shock cord so it doesn't move too much.
Okay, yeah, that's important. The bundle for the main needs to be when I use this technique, I sew the bundle, the blanket to the shock cord so that it can't move.
C'est vrai.
Pas sûr que j'ai compris qu'est-ce qui.
T'es la blanket autour, nous autres, on
le Nomex?
Le Nomex, mais nous
Ok.
autres, il tissait dans le corps des câbles.
Yeah.
Yeah.
Well, it's pretty much the same thought process, but yeah, I guess that's a good way to do it. Also, sewing the Nomex to the shock cord.
Yeah, they sometimes fail if the bundle moves, because then it can pull on the wires.
Yeah.
So a good way to prevent that is to just literally sew the blanket to the drogue. And then you're bundling both the main parachute and the harness for the main inside the blanket.
Yeah, that's something we can explore. We still need to sew the shock cord loose for the quicklings. So yeah, that's something we can do. But we'll try it, compare it with the method with the tie wrap tightly on the on the shock cord. We'll try both, see which one is better.
Okay. And what is the fitting that the drogue harness is attached to?
The shock cord is attached to U-bolts on both sides, which are in place in the bulkhead. So, normal 3/8 U-bolts with quick links. And on the parachute themselves, there's swivels.
And is this set up so that the electronics bay separates from the body of the rocket?
No. The electronics base stays inside this tube.
Okay.
It's held in place, if I'm not mistaken, it's held in place at both bulkheads, since one is acting as thrust and the other one is screwed in place, so there's no force acting inside the avionics bay.
Okay. Did you put a drawing of this in your progress report too? Do you recall?
I don't know. I don't think so. I don't think there was a question on drawings for this, so I don't know. I know we have the pictures from the CAD that we put inside the final progress the report.
Yeah, I don't have that.
I can probably share my screen with the assembly. It will help.
If you can, yeah, I'd kind of like to see how it's set up. I thought I had oh, wait a minute.
Non, pas encore.
Oh, I'm not going to be able to see that link.
Can you see my screen?
I don't know. I think I have an error here.
Yeah, I can see it.
Something happened. Give me just a moment to try to figure out what's going on.
I mean, I know we can see.
Okay, now I got it. I have it now.
Yeah. So yeah, that's the booster motor here. So that's the carbon fiber tube, and that's the fiberglass tube that we saw. So here is the avionics bay. So there's a bulkhead here and one here. So the harness connects to the U-bolt on this side. Here is the coupler, and then it connects on the U-bolt of the motor bulkhead on the other side.
Okay, and the drogue and the parachutes are located where?
Well, they're folded inside here.
Right in that area. Okay.
Yeah.
And so when the apogee charge fires, let's see. I mean, I think I have your drawing from progress report too.
I know we have a drawing of the that shows the geometry of all the harness and parachute on booster. I mean, on drogue configuration and on main configuration. Those ones I'm pretty sure we put them in the report.
Okay, I'm looking at the one from progress report too. And if I'm looking at this correctly, yeah, I mean, it looks to me like the interstage coupler and the electronics separate from the booster. And then the main is bundled near to the electronics bay, not by the boost, not by the rocket.
Well, I mean, the boost, what we call the booster in the, I can switch what screen I'm showing because I have it here. New Teams. Where's Teams? Okay.
Yeah, that's the one I'm looking at.
Okay, so this part, what we call the booster, I mean,
Right.
there's no fin showing, but this is the carbon tube, so the carbon fiber tube, and this is the fiberglass tube.
Yeah, so that's your AV bay down there. So your bundle is down there at that
so
location.
if
Yeah,
you can
okay.
see the foam, the parachute are here on the rocket, and the avionics base is here. So I mean, there is a separation here, but both parts of the rocket are still attached by the shock cord.
Okay. One thing, have you thought about if the harnesses are the way they are shown, that means that the main parachute is going to be underneath the fin can. And so when the bundle is released, the parachute could foul against the airframe. Have you thought about maybe making the harness length from the booster to the drogue longer than the harness from the drogue to the AV bay?
But well, that's something we can change. Like the 20 feet measurement, it's not locked in place. Like we can change it to have the main parachute at least be at the same level of the booster. Because that could be some, if they're all aligned, yeah, the main could be right under, and when opening could catch in the fins.
Yeah, so I mean, it would make sense to me just to switch the two dimensions, 10 and 20, just switch them.
Yeah, we only did this because we didn't want the like the main parachute and the AF bay having contact with the booster. That's the thought we put when we decided the length of each shock cord. But yeah, that brings other problems as we can see now.
Well, you don't want them to hit against each other. You just have the longer harness so that the booster is hanging underneath the bay and the bundled main.
Yeah, the only fixed measurement that can't really change is the distance between the main parachute and the avionics bay, like about 5 feet. Because I mean that's the cable. If we put 20 feet of electrical wire, there's more risk of having bundle and everything getting stuck. But yeah,
I'm not saying them to change that.
yeah,
What I'm
having 20 feet, like I mean, just quick, we are having 20 feet on the right and 10 feet on between the drogue and the main,
yes,
or something like that.
yeah, and so that when the main chute opens, it's above the airframe and not below it.
Yeah.
I mean, you can look at it, but I mean, if I was setting this up, I would switch those. You know, so it's just less, and I also use, I don't know if you've ever seen them, the Valkyrie drogues. Have you ever heard of the Valkyrie parachutes?
No.
Okay. Well, in that case, never mind. They're a parachute that doesn't have shroud lines, so it's less likely to tangle than a normal parachute. But consider just switching those two distances so that the main chute is above the booster, not below it. Because if it's hanging straight down, then it's more likely to tangle.
Yeah, catching the fins and stuff. All right.
Yeah, if it's falling very fast, it may not matter. It may be kind of flying around and not hanging directly under the drogue, so it may not matter.
Well, it does fall pretty much at the maximum speed allowable. We're at 35 meters per second. But
Okay.
we'll still probably change it because it's a risk.
It's easier.
Yeah, it's pretty easy. We just switch the length, do the knot on another place, and that's it.
Okay. Let me think if there's anything else on the booster. Did you show the interstage coupler? Is that carbon tube you were showing?
Yeah, that's the interstage coupler that goes. Well, we can switch sides to show it on the sustainer. But it goes. That's the motor casing right here,
Uh-huh.
and it goes around the casing.
Okay, and do you have like centering rings then over that coupler?
Yeah, there's going to be one centering ring about here, and at the bottom there's the bulkhead as a metal part that goes inside and retains and also retains like the coupler in place.
Okay.
And that part that goes inside is the one that pushes on the casing of the sustainer.
Okay. And are you using a separation charge for the stages?
Well, we are evaluating it because the only place we could put it is inside the coupler, and that would mean that the separation charge would blow directly inside the motor, which is not pretty optimal. So yeah, we're seeing it with that, and if we don't do it, it's just gonna be by drag separation, or and worst case scenario is hot staging in flight.
Okay. It's fairly common to build some sort of a cap to cover the motor to protect it during a separation charge if you wanted to do that.
Yeah, but doesn't the cap bring risk at the motor ignition since there's a buildup of pressure inside that could shoot out the cap and the igniter before the motor is lit?
Well, this is a little bit complicated, but usually, I mean, the idea is to have a cap that is on there for the separation charge, but then can pretty easily come off when the motor igniter fires or when the motor itself fires. You're really not trying to use it to build pressure in the motor.
Yeah, no, I didn't mean like using it to build pressure, but pressure does build inside the motor if there is a cap. And I mean, last year we just, I mean, from I think your your advice was to leave space in the cap so that it does not shoot out with the igniter before the motor is lit. So yeah, that's the only concern.
Well, yeah, and that's sort of the other part of it. I mean, you can I don't know, are you planning to hold the igniter in with a stick or something like that?
Yes.
Yeah, the trick is to have it so that the stick is retained in the motor, but the cap can come off.
Okay.
Does this, did you want, did you follow what I said?
Yeah.
Okay.
Well, I don't have the exact way of doing it right now, but yeah, I understand the
Well, you could be very inventive. Um, uh, I have actually used like Kevlar thread, and I'll glue it inside the motor, like in the nozzle, and then I'll wrap the thread around the stick and glue the thread to the stick so it stays in the motor. And then the cap can come off and the stick still stays in.
yeah, I think we understand
But
it.
you know, if you I don't particularly like to have it so that the motor blows off the booster. I think you should try to avoid that if you can, because you know, that can affect then the recovery of the booster depending on how it all goes.
Yeah, well, that's I mean, that was the worst case scenario of the drag separation. Last year
Yeah.
we did drag separation, so we calculated the difference in friction forces on both stages. With the fit of the coupler, so there's enough forces from the booster fins, the drag of the booster fins and the base drag of the rocket to pull on the booster by itself.
Yeah, I mean, most of the time rockets want to drag separate. The variable that you have a harder time controlling is what if there's any forces that are causing the two sections to bind together, like if there was any sort of a torque on the stages or something, and so they, you know, from the wind, for example, I mean, it might tend to keep the stages together. I think I just heard from Adam, just a moment. Yeah, he's not going to be able to join, so we'll just continue. That's my only concern. You can sometimes, if the stages, you know, the force that you can't estimate is the one that's you know, if there's a side force that's holding the two sections together and prevents them from drag separating.
André, ton micro est ouvert. Tu peux le muter.
Why not?
Sorry, Jim. Yeah, well, I mean, we'll check out the cap, because yeah, the only problem we saw was having the charge pop inside the motor, which yeah is not ideal. If there's a way to protect it, I mean, it's better to have the charge because we can really decide the timing of the separation, which is more optimal for the flight profile and the apogee prediction.
Yes, I mean that's why I do it. You know, I'll put a cap on the motor so that it doesn't pressurize from a separation charge, and then be able to control the timing of the separation with the, and you know, and if you have that cap on there, it can be a very small charge. You know, half a gram to 1 gram is usually enough. You know, if you want to drag, if the tendency is to drag separate only, then or if it wants to drag separate, then usually a very small charge is enough to make that happen. And then, like you say, you control the timing. I'm not saying that you have to do it. I'm just saying that you know, I typically would do it if there's some, unless there's some reason that you can't do it. You know, just for all those reasons.
Well, the only reason we were not sure is really because of the placement with the motor. Because we have the space and we have the channel on the altimeters, we have the altimeter for it. Because it was planned to have one. We were not sure at this point just because of the motor. But everything we have can let us put one.
Okay, how are you getting the igniter into the motor?
Well, there's a wire that goes all the way from the sustainer avionics bay, goes through a parachute bay and the payload, and then goes through some channels inside the last two containing the motor. And at the end, there's some small cable from that Victoria showing.
Yeah, so these are basically line flat connectors. We'll solder each and every strand together so there's less resistance, and we'll also have two of these connectors for each way, so they're redundant. So in total, we'll have 4 connectors that will like this. The reason we're doing this is that there's not much place between the motor casing,
Yeah, the after ring.
whatever this is, and the this. So that's pretty much the only reason why we use flat connectors instead of just normal wires, and the rest of the sections are just regular wires.
Okay, yeah, those look really thin.
Yep. Well, that's why we'll have two per. Well, you know, you have 2 wires to ignite the motors. We'll have 2 of them per wire. So if one of them breaks or scratches, then we still have another one for each wire. And notice that there's like a lot of different strands. So if there's like a partial cut, the current still flows inside. And as I said, we'll solder each and every strand together, so it's like one just wide cable and flat.
Okay. What are those called, if I might ask? Is there a name for them?
I think they're just flat connectors or ribbon cables. Is that it? I'm not sure. I'm not the one that bought them, but I think they're pretty standard in electronics.
Okay. Well, with that approach, I mean, you do have the option of using a separation charge if you want, because you could bring it down with one of those cables, and then it would just go to a small separation charge, and you'd have your igniter would turn the corner and go through that cap. You know, if you wanted to do that, it would be easy to integrate that into that if you wanted to.
Yeah, but the separation charge that we planned was coming from the booster avionics bay. Because then it can be bolted on the bulkhead of the booster, and there is no physical connection between both. But yeah.
Okay, you could do that too. All right, Zach, do you have any questions? Anybody else have any questions about the booster?
So looking at the booster fins, are you guys gonna have, what is your speed at separation, or sorry, max speed for your booster?
Jeremy, do you know this speed by heart?
It's close to 300 meters per second.
Okay. Is there any concern, Jim, looking at those fins with that foam core, with that foam being exposed to the sides like that? Would we want them to kind of put a cover over that, at least along the leading edge, to avoid a potential delamination?
Yeah, could you show us that leading edge?
Yeah, well, the foam core is when we glued the skins to the core, everything was done under vacuum, so the core is pretty much there's a lot of resin. It's a porous core, so there's a lot of resin in all the gaps of the core to keep the skins attached. It's core made for composite sandwiches.
Okay, you usually at this point we say, yeah, put that on the ground and stand on it and convince us it's very strong. I'm kidding.
Okay. Well, we're confident it's strong.
It's been done
Really
though.
strong.
People have done that before. So
We have
you're
one model in our shop, and we put a lot of force on it to break it.
okay. You're pretty confident that they're strong enough for that speed.
Yeah, and the flutter speed, we did some calculation with some composite. Specific composite calculations, and we get our shear modulus gives us a 2.07 safety factor. Since there's a 45-degree plies, there's a lot of strength in traction, in torsion, and the 90-degree plies gives it strength in flexion.
Okay.
And then the other thing I was wondering was attachment of your rail buttons. You guys just doing through bolt with nut on the back side, or?
Well, the very last at the bottom is screwed inside the truss plate, so
Okay.
we have 4 tabs in the truss plate. I mean, one of them is for the rail button screw. Then here there is a centering ring, and inside the centering ring we put the flange nut of a rail button, so it screws inside the nut.
Okay.
And the last one, it's screwed in one of the holes of the bulkhead, so also in aluminum.
Okay. I was just wanting to make sure that they weren't just, epoxied on and left as that. At least there's something else to retain the structural of them.
No,
There's
they
been too many
all-
times where even when I was in school and we had smaller diameter rockets that we go and put on the rail, and the rail would hit the wind or something and the buttons would just shear right off, and then you'd have to scrub for the day. So we definitely don't want that happening as we're out in the desert.
No, it probably won't happen. They're all screwed inside in metal.
Okay.
And so you'll be using those 3 buttons and what's roughly the total length from the first one to the third one?
Which one? The third one. I mean, the total length between from the one to the other was 54 inches.
Okay, that's good. I like that. If they're too far apart, I get worried about if the rail flexes, it can kind of pull on the buttons, but I think that's a good compromise between protecting against rail bending, but still giving you some, protection over the 2 lower ones, I guess is the way to put it.
So since the rocket is pretty long, I mean, we have 3 to help hold the weight, and then having 3 also helps with the effective rail length.
Yeah, I like that. I like that design. That's good. What motor? What's the booster motor?
N4000.
N4000. Okay. That's the Aerotech N4000, or
Yeah.
I'm sorry, say again.
Yes.
The Aerotech one, okay.
We have two Aerotech motors, the N4000 and the N1000.
Oh, okay, that'll be fun. That's always a fun fun motor to watch.
Yeah, there's a long burn.
All right, I think I'm good with the booster. Are you good with the booster, Jim?
Yeah, let's go on.
All right, let's go on to the sustainer. Or either that or electronics, however you guys want to do it.
So you mets électronique, fait qu'on peut faire la fin.
Well, we go into the sustainer. It's pretty much the same electronic for the sustainer and the booster, so we'll do it after that.
Okay.
So as said, the thrust from the booster goes to the aft ring of the casing and then through the sustainer motor casing and all the way to the to a bulkhead right here, which has 4 screws to then give the thrust to the rest of the rocket and the airframe and everything. There's aluminum fins and aluminum centering ring to hold them with the channels for the igniter wire. There's another centering ring. I think there's another centering ring about here, if I'm not mistaken. And then the motor is connected to to the bulkhead with a forward thrust. So the plug end of the motor goes inside a eye bolt. Then we have a super big parachute bay because there's the main parachute and the payload that goes in it. Since the payload is deployable, it deploys with the main parachute shock cord. So those are between the bulkhead and the avionics bay. So about this length, there is everything.
So let me ask, it's a deployable payload. And when is it deploying?
With the main parachute.
With the main, okay.
Peux-tu en parler plus sur après ça, qu'est-ce qui se passe?
Do you have any further questions for the deployable payload? Maybe I can explain what are the
Yes,
steps?
we'll have questions on that.
Okay. Do you
I
wanna
just
wait?
wanted to understand what you were doing as you were describing it, so that I would not, I'd be able to understand better your description. But yeah, we'll definitely want to talk about what the payload does and how it's recovered.
There's Adam.
Okay, perfect. So maybe they can finish with the sustainer and after I'll
Yes.
explain payload.
Uh-huh.
Yeah, so the payload goes out with the main parachute. It's getting pulled out with the shock cord of the main parachute. This shock cord, so the harness is connected to the bulkhead at the bottom which is a eye bolt for the motor. So yeah, it's connected with a quick link to the eye bolt and then connected to the avionics bay with a U-bolt. The avionics bay is inside this coupler with a switch band. And above that, there is the another parachute bay for the drogue, which is inside the nose cone. I mean, I think that's pretty much the whole part of the sustainer. We're missing the nose cone. We're fabricating it Monday with a outside composite company. And yeah, the whole rocket is getting finished this week for painting next week.
Okay, maybe go ahead and show if you have that same recovery drawing. Let's look at that for the sustainer.
Yeah, I have it.
Okay, so initially putting out the drogue on the right-hand side there, okay? And then, let me see, so when okay, so the payload is deployed, but it's tethered.
Yeah, well, the outside CubeSat is tethered. The payload does come out of the CubeSat.
Okay, so there's a piece that's not shown here then for the payload.
No, the payload itself is not shown in this diagram.
Okay,
Oh, the rover part that's getting out. It's attached to a 24-inch fruity chute, 30-inch parachute.
you referred to it as a rover?
Well,
Yeah, well, there's two parts for the payload, and the part that's deployed is a rover.
Okay. So it will land on the ground and then do something?
Right.
Okay,
And move around, and we have a camera and a LiDAR on it.
a camera and a what?
Obstacle detection. I'm not sure how you call that in English. It's
LiDAR.
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 Oh, okay,
LiDAR. Sorry.
okay. When does that operate? When it's on the ground or when it's coming down?
When it's on the ground, everything is activated when it hits the ground with sensors.
Okay. Right, so let me see, we've got the. So the av bay is going to come out and along with the main. And so how is the parachute being retained in the airframe before it's deployed?
it's well the section half bay is held to the rest of the tube with shear pins.
Okay, and
So
you're
the
not
fiber-
worried about the drogue pulling that off?
Well, there's not much force with the drogue.
Okay,
It's pretty much like if we had the drogue in the middle section and the main parachute in the nose cone, and the nose cone was held with shear pins. It's the same way.
okay, so when the so where are the charges for pushing? Like what pushes the payload out? Does it all come out at the same time with a charge, or how does that work?
It's naturally ejected. So the mains shock cord is coming out with the CubeSat. And then when it's at full tension, the rover is going to be ejected out of the CubeSat and not the other part of the payload.
Have you ever done this before?
No, this is a first for us.
And so you're probably not going to get a test of it before the competition.
Well, of the full deployment, maybe not, but we're going to test separate parts of the steps.
It's the tension in the shock cord, from the weight of the bottom part of the sustainer gets the shock cord in tension, so it strains out and pushes the rover. So yeah, I mean, it probably will be tested when the rover and the CubeSat is completed. Just having
Well,
tension on the cord and to see if it pushes it out. Okay,
Right,
okay,
yes,
it
yes,
is,
that's going to be tested.
Okay, all right. So so how is the drogue being deployed? Is that black powder or CO2 or what's the,
CO2.
you're using CO2 for that? Okay.
We have two CO2 at the top on the top bulkhead, so inside the nose cone. We have the primary and the redundant charge. And yeah, its job is to push out the nose cone of the rocket and break the shear pins to release the drogue.
Okay. Okay, so now I see the orientation. Maybe we can go back and just again show kind of that part of the rocket.
Yeah, so as I said, the nose cone is gonna be here at the very top. That's the coupler which holds the avionics bay. So on this side, there's the drogue. So there's CO2 charges. And on this side, there's the main compartment and the payload with the black powder charges.
Okay.
Inside this whole fiberglass tube, there's gonna be the main parachute and the payload. So yeah, that's pretty much. Apart from that, there's no permanent structure inside this tube. This coupler is gonna be it's semi-permanent. It's gonna be permanent in flight. It's gonna be screwed with normal bolts, so it doesn't release during the flight. But we're not gonna glue it in place to have access to the bulkhead. And yeah, on the final tube, so here is gonna be the bulkhead, which gets the beginning of the motor.
And how you said how is the I think you said there was an eye bolt right there at the top of the
Yeah,
motor.
here at the top of the motor is going to be an eye bolt because the forward closure of the motor is a single screw, so we cannot put a U-bolt. So the eye bolt acts.
Truss.
Yeah, acts as the what retains the motor in place, pretty much. And on the other side, we put a quick link for the shock cord.
Okay, and how are you preventing that eye bolt from unscrewing?
I'm pretty sure there's another screw on the side just to hold one side of the eye bolt. Your usual Kevlar thread trick.
Okay, all right.
And on the main parachute, there's a swivel link because on all parachute we put a swivel link, so that also helps from having rotation in the shock cord, and also the shock cord being pretty long, it's gonna be hard for it to put torque on the eye bolt. So yeah, the Kevlar is the side piece, like the thread, is really a protection, but it is not designed to have much torque to unscrew the eye bolt.
Okay, before we leave recovery, let's go back and look at that drawing one more time. Okay, so the one thing that I well, tell me what the drogue chute is.
It's a 24-inch elliptical chute or fruity chute.
Okay, so 24-inch elliptical, and how fast is this descending?
Well, at the end of the descent, so near the main, it's a bit above 20, like 23 or 25, if I'm not mistaken, meter per second.
Okay, so 25 would be 82 feet per second. Does that sound about right?
I mean, it's also inside the report, so I can confirm it. Drogue. 24-inch elliptical. 29.
Okay. Yeah, so it's coming down pretty fast. I mean, usually with a deployment design like you have, you in order to get it to come down without being too fast, it has to be a little bit larger than, for example, a drogue that comes out of the middle of the rocket. And so the concern that I always have with that configuration is when the drogue is put out, you have the tendency to zipper the top of the tube that it's coming out of.
To sever the top of the tube.
Right, because the drogue is going to come out and it's going to go behind the rocket, right?
Yeah.
If the rocket has horizontal velocity, it's going to come out, it's going to go behind the rocket, and it's going to try to, well, the harness is going to rub against the top of the airframe.
Yeah, there's not much airframe at this part. It's almost like a zipperless coupler. There's like maybe 2 or 3 centimeters of fiberglass above the bulkhead.
Okay, almost, but not quite.
Almost, yes.
You have a zipper shield also?
Yeah, we can put some zipper shield. We have a zipper shield that we print out of TPU and wrap around the shock cord. But at this part, I mean, it's probably gonna be the edge of the shock cord or the quick link that's gonna make contact with the tube.
Okay, well, this is something to pay attention to, because and the reason for that is that if you were to have horizontal velocity and there was a sharp edge there on the edge of the airframe, I mean, you could sever the harness. Okay, and so now the rocket comes in ballistic, the whole section. And so this is from a safety point of view, this is a real important part of the design, because you need to make sure that you do whatever you can so that you don't sever the harness at that point so that the rocket can come in ballistic. So there's many things that you can do. You can do what you said, sort of a zipperless cover over the harness so that it protects the harness at that point.
Yeah, well, that's what we use normally. It's the easier option. We just put it around the shock cord. It's something that's malleable, so it can bend around the corner, but gives it a wider area of contact with the tube to protect the tube and also to protect the harness.
And then another very easy thing to do is just to make sure that the tube at that point is rounded.
Well, it's pretty thin. It's hard to
Well,
round it. It's like 1.5 millimeter of fiberglass. So
right. Well, you can still round that so that you don't have a sharp edge. You know, if you had a very squared off piece of tubing, you know, you'd have a sharp edge there. And it's easy just to sand that a little bit so that you remove the sharp edge.
Well, yeah, it does. It is pretty sharp.
Yeah, well, yeah, I understand it's going to be thin tubing there, but you can still sand off a little bit, you know, just chamfer the edge of the tubing so that instead of acting like a cutting surface, it's more of a blunt surface. You know, even though it's thin, it still helps.
Okay, well, we'll also check on which part of the harness will or could come in contact with this tube. With the assembly of the bulkhead, the CO2 deployment system, and the quick link and everything, which part would make contact. We'll check it out and we'll act on it with either sending a bit or probably with the zipper shield.
Yeah, just be able to address the question because you will absolutely be asked, what are you doing to prevent the harness from being severed in the event that you have horizontal velocity? I mean, if you are, I mean, when you fly to 45,000 feet, you could easily have very high horizontal velocity. And so
Yeah.
now the drogue is deployed and you have a you know, a significant force on that harness. And we're going to want to know what are you doing to prevent the harness from failing at that point. Because if it does fail, now you've got a ballistic recovery for the rocket. You know, I don't care so much if the main comes out, but I do care a lot if the rocket comes in ballistic.
I think there's also a redundancy in the Blue Raven. If it detects it too high of a speed, it ejects the main parachute. I think there's a safety on that. But yeah, we don't want the drogue being left off in the air. We want to have a nominal flight.
Yeah, another common thing to do is to take the harness and this would be the harness between the main body and the drogue, and Z-fold that and put some like some electrical tape or something around the Z-folds so that it sort of acts as a shock absorber.
Yeah, we always do that.
Okay, yeah, that helps protect the drogue chute itself from shredding. You know,
we do it for some shock absorption, and we also do it because it prevents having the cord being tangled inside the bay. It's also make the packing more compact. So there's a lot of benefit from doing some folds.
Right, but there's a difference between doing that with something like blue tape or thin tape for organization versus putting tape on there that actually dissipates force. So it doesn't help you all that much if you just have like a wrap of blue tape that keeps the shock cord organized. If you're going to dissipate force, you need to have more than that. And then that needs to be tested. So, you know, I'm not sure how you are doing the Z-folding, but you can test that and you can decide if it's really dissipating much force or not. And you might find that if we do it a little bit differently, you might actually dissipate force a little bit more so that the drogue is not shredded. And you know, you don't have to do a lot, but you know, you want to have enough force there so that you have to pull pretty hard in order to get the Z-fold to unfold. You know, it's more than just a wrap of tape to keep the the shock cord organized, it actually dissipates some force. So that's something that you can just look at and you can say, okay, could we do a little bit more so that we're actually dissipating force? Because if you get a lot of horizontal velocity, that may be the difference between everything staying together versus having a ballistic deploy. It's very cheap insurance.
Okay. Well, we'll do more. I guess we always put it on when we do ground testing for ejection, and then we also see if the ejection charge, when it's big enough, sometimes it rips some of the tape, sometimes some stays. But yeah, we always do that technique to prevent what you talked about.
Yeah, and you would in an ejection charge test, you would want to see those Z-folds not break, because there's almost no force on them during an ejection test. It's only the force of the nozzle coming out. And if you were doing this for shock absorbance, you would want to arrange for it to require more force than that. I mean, you have to go through a calculation and you have to say, okay, if we were moving at 200 feet per second, how much force could that drogue chute generate? And then you would want to say, how would I Z-fold this in such a way that some fraction of that force would be dissipated?
Yeah, we have done that calculation. Where is it? It's right here. We have done the calculation for many scenarios, good and bad scenarios.
Okay.
So yeah.
Okay, so I see drogue at apogee and then drogue late apogee. Is there a velocity associated with those?
Well, not in the table because that's the results of the analysis, but drogue apogee is like the primary charge, and the late apogee is if it doesn't open at the first charge and open at the redundant charge. So the total velocity is higher on the late apogee since there's the sideways velocity and begins to descend. So there's also horizontal velocity.
Okay, well, I guess that's my question. How much velocity is there in that calculation?
Yeah, it's the velocity from the simulation, the total velocity at those points. So horizontal plus vertical. The numbers are not specifically written in the table since, yeah, as I said, that's the results for the forces.
Okay, so is that like a simulation where you launched it at an angle?
Yeah, we put the simulation I did was launch at an angle, and I put the maximum amount. Well, it was done with multi-level wind with well, not real data, but model data from an API that gives us a typical multi-level wind from the launch site. So we have a simulator that do loops of testing, and we have the data. So we put the maximum amount of wind, like where we could launch, which would give us the maximum amount of lateral velocity. So that's the worst case we can simulate and calculate.
Well, yes, except in your actual flight, it could be much higher than that.
well, if there's more wind or more angle in the rail, or just a problem in flight.
Well, let me ask this question. On your sustainer ignition, what is your maximum angle? I mean, is it like 15 degrees or what would be the lockout angle?
Ah, c'est quoi dans le programming le maximum angle?
Tilt lockout, you mean?
Ouais.
That's 20 degrees because it's the maximum allowed in the DTEG.
Okay, so if you were the calculation that I would suggest that you do is to go back and look at the simulation that generated the numbers in the table and say, okay, what is the velocity that the rocket was at horizontal, or well, I mean, actually both, I mean, it would be horizontal velocity. So look and say, well, what was that horizontal velocity? And then do a second simulation where the sustainer lights at 19 degrees. Okay, and then say, well, okay, now what is that velocity? Does that make sense?
Yeah, well, that's what I was trying to recreate, but with the wind, since open rocket doesn't give like you can, I don't think you can put like an angle for the lighting of the sustainer. It's automatic from the launch. So I was
Well,
trying to recreate that with having more wind, with which would push the rocket at an angle.
Well, imagine that I mean, the way that I do this simulation is I simply change the launch angle. And just keep increasing the launch angle and check what is the sustainer angle at the moment that it ignites. And you just keep, I mean, you might end up needing a 12-degree launch angle to get a 19-degree angle when the sustainer ignites. Does that make sense?
Yeah, yes.
And then when you get to a 19-degree launch angle, then look at the horizontal velocity at apogee. And it will probably be much higher. Right?
Yeah. I mean, it could.
And so if you're allowing the rocket to be at 19 degrees when the sustainer lights, then you need to look at the forces on your recovery system in the event that actually happens.
Yeah, well, that's we will need to check back the simulation where we put the winds in it, because I don't have the total velocity on top of my head, and I don't have the angles at which those happen. But we have the simulation, so we can check it.
And those are numbers that you should look at. Because if you're going to allow it to light it at 19 degrees, then your recovery system needs to be able to handle that recovery.
Yeah, well, there's
And
there's also safety factors above those numbers, but yeah, we will check it.
because the common failure mode with the deployment method that you are using is when you get that angle and you have the high horizontal velocity at apogee, and now it just rips the sustainer off, or it just rips the drogue off the sustainer, because you might have 200 or 300 feet per second of velocity under that condition. And so you sort of have that becomes your worst case. If you said, well, I'm going to have my lockout at 15 degrees, then you would do the simulation at 15 degrees, and you would say, okay, now what is the force on the drogue? And I suspect that you'll find it's higher than what you considered in the simulation where you added some wind. So all I'm saying is look at those velocities and then say, well, okay, how much force do I now have on the drogue chute when I deploy the drogue and I have you know, 200 or 300 feet per second of horizontal velocity. Now what force do I have? And you might find at that condition that it would be helpful to you to have some shock absorbance in that drogue.
Yeah, I'll try to just pull out the simulation on my computer while somebody else talks about maybe the payload or the avionics. I'd like to give you a number, like a horizontal velocity number that I have, like before the end of the meeting.
Okay, well, if you can do that, that's fine. I mean, you don't necessarily have to tell me the numbers, but I just want you to look at it and think about it and say, well, what happens, you know, if we're going to allow the sustainer to light at 20 degrees, it's very common for sustainers to be close to the angle that you set. So, you know, you may go through your simulations and you may say, well, okay, we're at 8 degrees or 9 degrees or you know, some small angle, but very often you're close to that maximum. And so if you're going to allow that, you have to have the recovery system designed to recover safely if you do that. So you would look at the simulation that you did, but you would also do another simulation where you just keep increasing the launch angle until you're actually at the 20 degrees that you're going to allow. I mean, you could do that, I mean, because you don't always, it's difficult to get there unless you just literally have to change the launch angle in order to get to that 20 degrees at the point where the sustainer lights. And then you want to look at the horizontal velocity that happens when you do that. And it may be much higher. And then that's the point that you want to be able to say, okay, we understand the force on the drogue, and we're going to design for that force.
Good.
You know, and so if you can do it in, you know, here in the meeting, that's fine. But if you can't, just look at that. And I mean, just as an example, if you said, well, okay, the simulation that I did here, I was at 80 feet per second. But if I do the 20 degrees, I'm at 200 feet a second. Well, then you need to consider the forces at 200 feet per second because it might happen.
Okay.
And so, you know, when you're doing the out the top deployment, and you know, that you really need to look at that part of the flight, because that's where you could strip the drogue or you could sever the harness at that point, and now the rocket comes back ballistic. And from a safety review perspective, that's the number one thing we look at.
But we will need to be pretty fast for it to have a higher pound force, because I'm pretty sure the angle from the simulation is probably in the near 13, 14 degrees. So gives us a like horizontal velocity probably near the, I don't know, I'd say above 100 feet per second clearly, maybe 200, 150 in that ballpark. So to have the pound force go up like an order of about 5-6 times maybe to have the, yeah, it's a high speed.
Okay, well, just look at it. I mean, as you say, I mean, it takes you 5 minutes to do a simulation to see that. So, you know, just run the simulation to where your sustainer is lighting at 20 degrees and, you know, and see what that gives you for a horizontal velocity at apogee and how does it compare to the numbers that you used. You know, it's so simple to do that you know, you just need to look at those numbers and say, okay, what does that change our opinion about what we should do in the recovery?
All right.
Okay, I think the next thing is we just want to look at the electronics bay, right, Zach?
Yes, yeah.
All right.
So, as we stated earlier, the electronics bay for the booster and the sustainer are very similar. So we'll go through the entire booster's bay. As of right now, we only have the booster's bay fully assembled. There's only the local wiring left to do. And we're currently in the process of assembling the second sustainer, well, just the sustainer avionics bay. So yeah, I think the first part that we can look at is the power system. So, this right here is our custom battery pack. It contains a total of 10 Li-ion 1S battery cells, and they're wired differently to give us 3 independent circuits for each of our different subsystems. So booster is this one. So yeah, there's 10 cells in here. The first circuit is the Blue Raven circuit, which has only, I think it's one, yeah, it's only one cell, 1S, so that's 3.7 nominal voltage. And it will be connected to the Blue Raven only on its own independent circuit. And the same goes for the Blue Jay altimeter, which is our redundant altimeter. So the Blue Raven is the primary altimeter. It deploys the booster and main parachute. And if we are to have a booster separation charge, the booster will also trigger it. Our redundant altimeter is the Blue Jay Plus. It deploys the main and redundant parachute. It's also important to note that I'm not sure if this is the right one, but I guess it's on the back. You can't see it, but we have bypassed the magnetic switch on the Blue Jay Plus to be able to power it through our power distribution system, which I will explain right after. It is a very slight modification that we've made, and we've also made this modification last year at the last IREC, so it is flight tested and we know it works. So this entire battery system has a BMS on top, which is custom made. As of right now, we are testing it, and it's not quite working just yet. So if we're not able to make it work, we might remove it entirely and put some commercial battery management systems, or even just let it run without BMS and just make sure that they're well charged before flight. So the next important unit of our avionics bay is this power distribution board right here. So for the entire arming procedure, we use push pins. I'll show you later how it works, but basically this is the power distribution board not assembled. Each assembly here allows us to put a screw inside and connect and basically press on each of the switches. So this is made to be armed from the outside, as you can see right here. I think this is the third, well, at least the second time we've done this. And the concept of having a power distribution board like this dates to our last competition, which was Launch Canada last year. So it is a flight tested and proven concept. So as I said, you just have a screw, and if you want to power this switch right here, you would press it inside. Now it's armed, and you just have to screw it in. So yeah, so what this board does is basically it takes power from the main battery system for each of the 3 independent circuits, and it redistributes power and it just arms all the systems. So yeah, the first two independent circuits are the two altimeters. The third independent circuit is everything SCAD related, and the featherweight GPS tracker, which is right here. So yeah, on the third circuit, we have a 2S, I think it's 8 cells in total, so it's about 7.4 volts nominal, and I think it's 16 point something amp hours in total. And what's on this circuit, as I said, there's a featherweight official GPS tracker. We have our student developed flight computer, which in this flight, it will be its first flight test. So we will test our new deployment algorithm for the next competition, but it's not deploying anything as of right now. There's also the cameras that are going to be on this circuit, and the radio that's connected to the flight computer using a cable, and also our SCAD beacon. That I'll show you the ground station later, but this is a really fun concept for recovery. But essentially, we're able to track the signal coming from this emitter in order to precisely locate the rocket after it landed. And well, we're aware that the 2S battery system isn't compatible with the featherweight, which is why we put a voltage regulator on this board to regulate the voltage on the featherweight to 4.2 volts, which is like the maximum voltage of a 1S battery. So we won't have any problems regarding power with this. That's it. Oh no, sorry, that's the booster. Okay, what I just described to you was the sustainer. Sorry, for the booster, we have the featherweight on its own. Yeah, okay, that's it. So on the booster, we have the featherweight on its own circuit as well. On the differences between the booster and the sustainer is that on the booster, the featherweight has its own independent circuit. It's on a 1S battery, lithium battery. And on the sustainer, the featherweight is on the SCAD power system, and it's powered through a voltage regulator. So back to the booster. I think that's about it. For the booster, that's about it. And now the difference for the sustainer, there's also a second difference, and that is we'll also have a Blue Raven on the sustainer, but we'll replace the Blue J Plus with a Stratolager, and the Stratolager will have a 9-volt alkaline battery. It's always what we've used with the Stratolager, so we're not going to change something that works well. In the sustainer, as I've stated, the featherweight is not on its own independent circuit. We found that was quite a risk, so we'll put an additional GPS tracker, which is the Spot Trace, and we have it right here. Okay. It's basically a commercial GPS tracker that's not really made for rocketry. It's more made for camping or stuff like that, but we've put it in all of our last rockets, and it works really well as a kind of a last resort plan. So yeah, that's about it for the entire system. All our wiring diagrams and block diagrams are in the report. Also in the sustainer, the reason why we have the featherweight not on its own circuit is because we have a switch specifically to shunt the igniter for the motor. So that's why we're using an extra switch to shunt. So we've had to put the featherweight on its own, on the main system. I think an interesting thing to note for as of a design perspective, we've tried to put a kind of different connector for each and every use. So the assembly, the assembly will be very much simpler than the other years because every single connector, every single different connector has its own use. So it's very unlikely that we'll plug a device into the wrong thing and break everything. So that's what we've tried to do this year. And I guess that's new for design choices. There's also going to be cameras around here. That's about it. So yeah, if I can resume the tracking solutions for both stages, we have the featherweight GPS tracker as our official tracker. We have our flight computer that will transmit telemetry, including GPS coordinates through the radio. The radio right here. And lastly, the recovery beacon that we'll use to recover at the very end. The recovery beacon uses, this is the receiver for our recovery beacon. It basically emits a signal in the rocket. It operates in the 70 centimeter band, and we'll receive it with this, and it beeps louder or less loud depending on the received signal strength. We've used this last year at the Launch Canada, and it works really well. So this is really useful to locate the rocket when we're in the last, say, 400 meters of recovery. You're around the rocket, but you can't really find it. This is really useful for the last few hundred meters. And yeah, in the sustainer, as stated, there's the spot trace that's also there for recovery. And yeah, we've looked at the battery life for all of our systems. The altimeters have basically unlimited battery life. We're talking like 210 hours, 300 hours. They're pretty overkill cells, so we're not worried about that. The main SCAD system, first of all, it has a lot more power. It pulls a lot more current. So current battery life is estimated at like more than 9 hours. So we're still not worried about this one. I do have the list of all transmitters in this if it's needed. And as of testing, we have we've done most of the bare minimum amount of work for the rocket to be safe to fly. So all we have left to do for assembly is, as I said, the local wiring. So basically doing the connectors for all the different components in the bay. So for the booster, that's all there is left to do. And for the sustainer, we also have to assemble basically. The bays are very similar, so it shouldn't take too long. And we'll also have to do the local wiring. And as of testing, we want to do the usual tests. So we'll test to see if the Blue Raven is able to ignite the igniter even with the flat connectors. This is, I think, the only thing that's more exotic about this design is those flat connectors. So we really want to test them to make sure that there's no problem. But I've done some calculations that I really don't think they're going to be much of a problem. Same for all of the the different recovery system, E-match or the cable cutters. And yeah, we've calculated the battery life. We'll try to do like a real test to see if that's actually what we get. But we have a pretty good safety factor, even if, say, the battery life is lower. And yeah, we'll also try to do a communication test when everything is up and running, as well as a range test for the range test for the way GPS trackers, but also for our radio and all the different custom systems. So yeah, I think that's all of it. Do you have any questions regarding this?
Yeah, the one question I have now, you said you made a modification to the Blue Jay. Did that involve like soldering anything to that board?
I think it was shorting the 2 pins on, yeah, I think it's a very common modification that's made even in, I'm not sure, but we found some documentation that details how to do it, but it's basically shorting the magnetic switch.
Oh, okay.
And we, as I've stated, we've done this last year as well during IREC, so it's we've tried it and it works well.
Okay. And how many total radios and transmitters?
Let me get you that question. I think it's
I mean, just in that bay there.
Oh, in that bay there, there are 4, if I remember correctly. Yes, so we have 2 in the 30 centimeter band. So that is the featherweight GPS tracker and the radio for our flight computer, which is the IFD 900X. An additional transmitter is.
I'm sorry, say that again.
RFD 900X. It's
Okay.
a common radio used for rockets and drones, but it
is. But now, how are you operating it though? Are you operating it to where it hops, or did you set a frequency?
As of right now, we plan to use it in mode B in the SRA, the section of the band plan. That is something that I wanted to ask you about. Do you think it would be better for interference purposes and just to make sure that we don't have problem? Do you think the mode A or mode B is more adequate? We thought of using it as mode B because by default it uses frequency hopping, but we can also configure it to have mode A and just be on a single wideband frequency.
Well, the issue, and I don't know the answer to this, which is why I'm mentioning it. Mm-hmm. But if you want to have it to where it hops, it needs to be within the frequency, within the SRAD frequency band.
Yep.
And I don't know if you can do that.
Yeah, I'm pretty sure you can state like a minimum and maximum frequency.
Okay, if you could do that, and the other issue with it would be, and again, I'm not an expert on this, as I'm sure everybody knows. I am not an expert on this, but there may be an issue at just being, staying legal, because if you constrain the number of the range, then you have to constrain the bandwidth, and you may not be able to have enough hopping channels to be legal, and I'm just not sure about that, the answer to that with that radio.
I specifically did not look at this in very much detail, but one of my friends who works on this has looked at how you configure it, and I did ask him about this, and I'm pretty sure you can configure like we've looked at the rules in the student band plan section, and we're very sure that you can do mode B, so frequency hopping legally with this transmitter.
Okay, all right, that's good, because I know there will be quite a few of them, and I'm just not sure what the answer is.
Okay.
But as far as which would be better, I'm not really sure. I mean, my guess is that if you can do the hopping, it might be better.
Okay.
As long as you can do it consistent with the plan.
Mhm.
You know, the thing just to recognize is, you know, I mean, we're trying to provide a single radio in the COTS band for each team.
Yep.
And in order to do that, that means that the SRAD portion of that band has to be relatively small. And so, you know, there's going to be a whole lot of radios that are going to be trying to transmit within that relatively small band.
Yes.
And so my real advice for avoiding interference is to try to fly early in the day, so there's not so many of them that are operating yet.
Okay, sure. I also, well, in the band plan section, it states that if we are to do mode A, which is wideband on a single frequency, we'll have our kind of own channel assigned. I'm not sure where exactly in the journey, but we will have our own clean frequency in the SRAD band. So would that be better, or
Well, what's going to happen, I think, and I don't really know how to anticipate this. I really need to see the progress report 3 data, but I think what's going to happen is that there's people are going to have so many radios that we're going to go through and we're going to start assigning them, to where each device has its own range. But what do we do once we fill that range? Now what happens?
yeah,
It may be that the teams that are in that position after the band gets full are not going to be able to transmit. And so in that case, you'd want to be able to hop so that you're not dependent upon getting that frequency.
Yep.
Now, on the other hand, if you go early in the day, you might have better luck doing it that way. If you're later in the day, you might not be able to get that frequency. I think one other thing that's going to happen is that, we're sizing the COTS band for like the worst day when we have the most flights. And it may be that on a day when there's less flights, that we're able to allow the SRAD radios to encroach on the COTS band. So we make the SRAD band bigger and the COTS band smaller. But we're not going to know that until we're into until we're actually there doing it. As to what those bands are.
So frequency hopping would be safer if we want to avoid problems, well, unintended problems during the day.
Yeah, as long as you're able to constrain it within the range for the SRAD range.
Sure. Yeah, that works.
That's the most important thing, because we're not going to allow people to hop into the COTS band. Because we want to make sure that everyone has a frequency in the COTS band that is not encroached on.
Yep, that makes sense. So yeah, and the third transmitter is the the beacon, but it operates in the 70 centimeter band. And I think this one is mode C, so it's a narrow band on a specific frequency. And so these are the three normal transmitters and the booster and sustainer. And the sustainer, we also have the spot trace, but the spot trace has its own proprietary frequencies, so it won't interfere with any other team.
Okay, and for the 70 centimeter, do you have a ham license person?
Yes, we have two. I have one, and there's also someone else that will have one on place.
Are you able to change that frequency or is it fixed?
It's pretty hard to, well, we could make it easier to change, but it's pretty much fixed. So if we're able to have the frequency given to us in advance, it would be better. We can, I guess, try to make it easier to flash because you have to flash new code if you want to change the frequency. It's not very I know it's not very good to do it like that, but that's the limitation we have. But from what I understood, the 70 centimeter band is less populated. So if it's possible to have the frequency in advance for this, it would be very, very appreciated.
Well, the option, I mean, I'm not sure which way would work. If nobody said that, I mean, well, if you came and said, I can't change the frequency, the question for me is how do I know that and be able to give you that frequency when there's 200 radios coming?
Yeah.
It's hard to know that, but what we're planning to do is to basically say, okay, a team has a transmitter in 70 centimeter and it has this bandwidth, and we would assign you a center frequency. And this would be several weeks in advance. So if you said, well, okay, a couple weeks in advance, it's easier for us to change the frequency. So, so what I would say is just make sure that you're able to do that, but somewhere in the progress report, tell us that you have that issue. And I can't promise that we give you the frequency that it's on, but maybe we can.
Okay,
sure. If we just notice it going through that you want that frequency, maybe we can do that.
Okay, sure.
But at a minimum, we're going to try to assign everyone a frequency several weeks in advance so that you have the opportunity to go back and adjust it.
Okay, yeah, thank you. I have the information for this transmitter in the report, but I'll also include it in the progress report just to make sure.
Yeah, we're not going to have the reports.
Okay.
I mean, well, I'm going to try to get them. Right now, I don't. I'm going to have to ask for them.
Okay, sure.
But they're in sort of the judging side, and so I don't see them necessarily. So what you need to do is put them in your list and the PDF list in the progress report.
Okay. Yes, for sure. Yeah, good. You have further questions about the avionics bay?
No. Let me see. Let me think. I think we covered everything. The only thing that I wanted just to make sure was that for the igniter, you said you had a shunt, but I didn't hear you say you also had a disconnect. You need a disconnect and a shunt.
Just to make sure that we're on the same vocabulary, what specifically does the disconnect does?
The disconnect just opens the circuit to the igniter.
The switch.
Yeah, it's the switch. Attends.
Les gens qui posaient les shortés, c'était poser les shortés qui font les inverses un lot.
J'en ai aucune idée. Alex, sais-tu comment répondre à ça, toi? Ben, I'm pretty sure the switch does it, but
Il est pas là, oui.
Géo est pas là. Euh,
Yeah, it would need to be set up as a double pole, double throw if it was going to do that function, both of those switches.
then I don't think it's on. Is it a new rule?
No, that's been a rule for, I think, remind me, Zach, is the shunt the new rule for this year? I think the shunt is, but the disconnect has been in there for a long time.
Okay, because we made the same circuit as last year, so if the rule was there last year, I don't see why it wouldn't be here today. So so ça shunt.
Yeah, I can try to look real quick and just see if I can find it. What section is it? It's not there.
Because yeah, I think for the safety switch we have well, so it's not connected for safety, and then if you connect it to the board, it's by default it's shunted, and when you arm it, there's one switch that's different than the others that connects the strands to the Blue Raven. I don't see a disconnect, but is it perhaps like in some other place it may be on the en bas of
Yeah, I mean, I'm just, well, I need to, for some reason, I'm having trouble. I haven't looked at that section for a while, so I've got to find it.
I don't specifically remember seeing a rule for that. I do remember the rule for shunting though, so that's what we did. And as I said, we did it's the same circuit as last year. So if it was legal last year, it most likely is for this year.
Well, it depends upon whether or not someone asked about it specific last year. I don't know that. Why can't I find this?
So there is an example of one down in, it says Appendix D.
Yeah, but that's an example of a switch, and that's something we could look at, but I want to find the actual requirement here. Why can't I find that? Well, let me try Plan B.
I'm looking at 5.14 or so for the arming procedures. All projects include provision to open circuit between flight computer and air start motor igniter.
Yeah, that's it. So let me get back to there.
To open the circuit between the flight computer and the air start and to shunt the igniter. Okay, wait.
Can be accomplished using one or more than one physical switch.
Yeah, well, we've looked at it this way that the way that we shunt it makes it not connected to the flight computer. So the way we interpreted the rule, we thought that well, can show you the circuit here. Je pense on a dessus sinon le. Ouais. So this is the wiring diagram for the igniter. So we thought that if it's shunted right here, it's not connected to the Blue Raven. So we thought that basically that it counts as an open circuit, and then when it's connected, it's connected correctly. So does that Is that okay? If not, we can look at ways to change this. And
Well,
make,
move back in, but the camera's moving. I can't.
Oh, yeah,
I
sorry.
can't see it. So you're coming from the Blue Raven and you have a switch that it looks like a 3-position switch.
yeah, it's yeah, it is.
Okay, so yeah, I think it might be okay. I mean, if you yeah, can't quite tell what it's doing. What is, I mean, when you're showing the position that it's in right now,
Yes, so
is that with the pin in or out? Now this is the switch
is-
on or off, I guess.
yeah, this is so it's off, so the pin is out. So it's
Okay.
on right as of right now, it's shunted because the pin is out. So you can see that both strands go in and connect together. So that's the motor being shunted. And when it closes, then well, this strand would not connect to this one. So this strand would be connected to one channel and the other would be connected here to the other channel.
Yeah, I think that's okay. I'm pretty sure that what you're doing, it's okay.
Okay, good. Because yeah, as we interpreted it, this counts as being you know, an open circuit disconnected from the Blue Raven. So yeah, that's why we did it this way. So yes.
Okay.
But is there anything else regarding this?
I think that was it for the altimeter base. What do we got left? Zach, do we got anything left?
I think it would just be payload.
Yep.
The deployable.
Okay.
Yes, it is. I'll leave you with the.
I think
So
we're gonna hear
for
about
the
the payload.
yes. So for the payload, we have a 3U CubeSat format that's divided in 2 sections. So on the upper sections, we have an hyperspectral camera for chemical analysis of the air's composition. And the lower section is where the rover is. So the main parachute shock cord is well, it's going through the payload to eject, but it's not truly going through. It's separated in 3 different sections. And so that's what's going to eject the payload, well, the rover. And so once it's ejected, there's a fruity chute. It's a 30-inch that's going to, make sure the rover gets to ground safely. Once it's on the ground, there's a cable cutter that's going to separate the chute from the rover. And we have there's going to be weights on the parachute, like the rover's parachute, to make sure it doesn't just like get far away and it creates problems. So it's going to stay pretty close. There's weights and there's a SRAD GPS. The one that was presented, it's called the
Featherweight GPS tracker.
well, that one is in the rover. So the SRAD one is in the parachute. And so the second one, the featherweight, is in the rover. It has its own battery for reasons mentioned before. And there's also a PCB in the rover that, assures it's autonomous. Autonomous on the ground. And there's a 2S battery to, just for alimentation. And there's a run cam, a LiDAR for obstacle detection. The rover is designed in PLA or PTEG, right? And the wheels are made in TPU with honeycomb pattern, so for shock absorbance. And there's like a layer to make sure they're isolated from any like ground problems, branches, or whatever else. the rover can land on any side, even on sides. That's going to be tested later. So like the sides part is going to have to be tested, but whether it's on its back or upside down, it's going to be fine. It can roll. And yeah, there's the cable cutter to separate. And that's about it for rover, I think. Yeah, for rover events.
Okay, so when the rover comes out of the CubeSat, it's on the parachute, right?
It's not fixed to the parachute. It's like the cord is it's like at the back of the CubeSat. The rover is placed and secured safely, but not too safely, so it can allow ejection. And so when full tension is reached in the shock cord, that's when the rover is going to be pushed out.
Okay, and then but as soon as it's pushed out, the parachute opens and the rover
Right.
comes down.
Yeah, exactly.
Okay. Okay, so the rover lands, and the one thing that I heard that we need to talk about is that you're going to have a cable cutter on there that's going
Yes.
to release the parachute.
Right.
Okay. So, well, the one thing that's on the top of my mind is that represents energetics in the payload.
Yeah,
And
that's right.
energetics in the payload are not allowed.
Yeah, okay, I see.
Now, it's not a whole lot of black powder, but it's still energetics in the payload. So and if is it the same half cat?
Yes. Same thing.
Yeah. Yeah, I don't know about that. I mean, it kind of concerns me a little bit because if you've tested the half cat cable cutters, you know that there's quite a fire that comes out of those when they fire. And so that's something that could represent a safety hazard to someone on the ground if they came up and it didn't fire until they were there. Now you've got some energetics that could injure someone. It's I know it's unlikely, but the reason the rule is there is to not have energetics in the payload. So that's one thing that kind of occurs to me. I mean, is there a way that you can release your parachute without having to use black powder?
Well, there was an option of having like a longer, maybe a longer rope, so it can just like unfold and the rover can freely move. Other than that, for cutting the ropes, we didn't really have any other options other than the black powder, but we could test the option of the longer rope that unfolds. Or the rover could just like keep its parachute.
How far does the rover have to move to demonstrate what you want to demonstrate with it?
Really not far. It's gonna roll around and it's gonna acquire a bit of data. It doesn't have to go really far.
Well, that might be a better thing because if you put, an E-match and a cable cutter and those sorts of things, those are energetics.
Yeah.
And payloads are not supposed to have energetics. Other than what is specifically required for the recovery step.
An electric cable cutter? Is that a thing, an electrical cable cutter? Are you aware of something that wouldn't like require black powder?
Yeah, I mean, if you could figure out how to do it in a way that did not involve, the E-match and the black powder.
Okay, and are those
in the half-cat cable cutters, there's an E-match and black powder.
Right.
And that's what's not allowed. That's what would not be allowed in your payload. Unless it was for, I mean, if you put out a payload at apogee, and you needed I mean, you could put out a payload at apogee and then have two cable cutters releasing the main, just like you're doing in your rocket. And that would be allowed.
Okay, yeah, but the issue is more for the rover's chute, like while it's on the ground.
Well, but see, that's not part of the recovery.
What
And
do you
so-
mean?
If you're using an E-match and black powder to actually do the recovery of the payload,
Oh, okay, I see. So that's
That's
where it's a
allowed.
problem. Oh,
you know,
that's
it-
allowed. Okay.
Yeah, it didn't used to be allowed, but we changed it this year so that if a team needed energetics in order to do the recovery of the payload, that would be allowed. But to do part of the experiment, it's not allowed.
Okay, and when you say energetics, is that just black powder and the E-match, or is there something else that is involved in that category?
Well, I mean, I mean, energetics in the payload can include many things. It can include the on E-match or an igniter and black powder, but it also could include, like, if somebody had a compressed air cylinder or a coiled spring. Things like that are considered energetics. And those in payloads are not allowed.
Okay. We'll find a way. I think we can work something out with longer rope.
Yeah, that probably, that would be allowed because, I mean, it would be ejected from the CubeSat and it would fall a little bit, but the parachute would open. And then the rover would be falling underneath a longer, a longer cord, but that would be okay.
Okay, yeah, we have to make sure the parachute opens with the length of the rope, but yeah.
Right. So go check the rules and, make sure that whatever you're doing is compliant. But you'll see in there that for the energetics are allowed in the payload for the actual purpose of the deployment. But you don't have deployment for the way you're doing it because you're putting out the parachute, with the main.
Right.
And so, you wouldn't be allowed to have any energetics in the payload then. Batteries are okay, but compressed air, black powder, that sort of thing is not allowed.
Okay. We'll find another way.
Okay. I was sort of thinking, well, could there be like a servo way that you released the parachute? I mean, there's probably other ways to do it if you really wanted to release it. But from what you've described, though, just having a longer harness might be okay. Because
So
you're
there
probably
is-
gonna land.
So there is the Jolly Roger chute release, but that utilizes a LiPo. But I would assume you guys would probably be able to develop something to want that same system to detect a ground, because that only works at a minimum of 30 feet AGL. So I would assume you guys might be able to develop something that would detect ground contact and then just pull out a pin on itself that then releases it from the chute system.
But
That might
would
be an
great.
option.
C'est super. Ok, puis il faudrait l'adapter pour nous.
Ouais, mais ce qu'il dit, c'est tu fais juste tu peux trouver une façon avec un cerveau de le faire.
Ouais. Okay, we'll look into that. Could be another option. Thank you.
You have any more questions about the payload or anything?
Oh, did Jim drop?
Oops.
I don't know if Jim had any more.
Maybe he had internet problems and might come
Possibly.
back. Thank you.
Guess we can wait and see if he pops back on or not.
Oh, there it is.
C'est pas rentré. C'est parce que-
Et 2 heures, 2 heures et demie. C'est correct encore.
Il était là, mais demandé pour revenir, j'ai accepté, puis elle l'a pas laissé rentrer.
Le ban.
Well, no, he asked to come back. I accepted the request to bring him the call, and it just didn't work.
Huh. Yeah, I don't have any messages from him, so
Oh, try another time. Maybe now it will work. Oh, okay.
there we go.
I am back. Sorry about that. So I think that's all that I wanted to let you know on the payload. I noticed you stopped moving about the time we were talking about the Jolly Logic shoot release approach for kind of letting go of the main chute if you wanted to do that. But you can kind of look into that, but I think that the E-matches and black powder are not going to be allowed. So got to find some different way to do that.
Great.
Did we have anything else that we needed to do?
I think that was the last thing.
Okay, well, yeah, it looks like you guys are well along and looks like you're trying to win.
Yeah, maybe.
Oh, let's see. What I did want to just check with you and see if you had any questions on the programming for lighting the igniters. I think you probably did it last year. Adam sent out a document that had how sort of the process for that.
Well, yeah, as of right now, I think it's last year we did it timer based, and as of right now we're planning to do it this year again. Just want to know, do you think it's like a good way to do it? I'm not very familiar with the Blue Raven, but is there like a better way to do it, or is timer based just correct?
Well, tell me what that means.
Well, right now we have a timer set at, I think it's 8.2 seconds, is it? But essentially we after 8.2 seconds after I don't see output
I see
after.
the-
oh, so it's between 7.8 and 8.2 seconds for the timer after liftoff. And we also have, all these settings to prevent ignition if the flight is non-nominal. So if it's more than 20 degrees, and if it's not at 70% of the simulated altitude. And so I'm pretty sure that after 7.8 seconds, if all the conditions are met, it's going to ignite. I'm guessing that's like the normal way to do it. Is it the best way? Do we keep it that way, or should we do something else?
Well, what device is providing the timer?
That's the Blue Raven.
Okay, so you are using the Blue Raven for that.
Yeah, we are in both stages. So if there is a separation charge, the same process will be applied to the separation charge as the third option.
Okay, yeah, if you were to use the separation charge, you want to sort of not necessarily have all the constraints.
Okay.
Because I mean, if you're doing a separation charge, basically the only constraint you have is that the rocket takes off.
Yeah.
Because once you get to the point where you want to separate, you want to have that happen. I mean, you wouldn't want to have the separation charge, for example, constrained by tilt. Or something like that. You just want to have it go. And the separation charge shouldn't be, I mean, you want to have a half a second or so delay after motor burnout before the separation charge fires. So you would not want to have it fire as soon as the Blue Raven detects burnout.
Right, so half a second after
You've got to
burnout.
have like burnout plus a half a second, or you've got to have time from launch to be long enough so that it's a half second past the burnout time.
And what would be better to do the timer since launch? So we calculate how long the burnout takes and then write this plus half a second, or I'm guessing there is a setting that you can directly program burnout and half a second after. So which one you think is better?
Well, for a first stage, the advantage of doing it from launch is that you kind of control the time when it occurs. The only reservation I have about doing it from the burnout is that sometimes altimeters and burnouts are a little bit confusing. For example, if the motor chuffs, for example, now I mean, maybe the motor chuffs a half a second, right after it leaves the pad, and now all of a sudden your separation charge is firing, while the motor's still burning.
Yeah, okay.
That's not so good. So the other thing that can happen is that sometimes burnout is not detected exactly when you think it's going to be. So for a commercial motor, I'll normally set it for time from launch.
Okay.
Just because commercial motors are pretty reliable in terms of the amount of time they burn for. And then if there's a problem detecting burnout, you're not affected by that. So that's usually the way I do it. And so otherwise, I think, I think on, using the Blue Raven for this, you have to use the custom programming screen in order to do all that stuff. Don't use the two-stage default programs that the Raven has. You have to use the custom screen. But it sounds like you're doing everything that you need to do for that.
Yeah.
I was confused when you initially said you were using a timer. It's like,
No, we're not. Sorry, it's that. Yeah, it is the Blue Ravens timer. Yes.
yeah, okay. So that sounds okay.
Okay. Yes. So yeah, for booster, we're doing that, and I'm guessing for ignition, you know, the Blue Raven timer base is a good option as well.
Yeah, no, I would only use one timer. I would only use one Blue Raven to do that. You know, one igniter, one circuit. I think you might be using two.
For igniters,
Yeah,
no, we're just using one. I
Just-
don't think
just
we're
one.
allowed. Yeah, we're not allowed redundancy on the igniters.
well, you can, but I don't recommend it.
Oh, okay, sure.
But I was wondering because you said you were using 4 of the conduit.
Yeah, no, there. What I meant by that is we only have one pair of wire going through to lit the igniter. The thing is, I was worried that maybe one of those cables either might not be enough because there's too much resistance, but shouldn't be a problem. But what if it is? And if one of them breaks because they're so thin, then each cable in the pair of cable will go through 2 of them just to make sure that a single flat cable breaking isn't disconnecting the igniter completely. So it's still one pair of wires. It's just that we'll use 2 pairs of flat ribbon connectors to really make sure they don't break.
Okay, I think that's fine. Yeah.
Okay, sure. Okay, good. I think that's all the questions I had for this.
Okay. I don't have any more. We've gone for a while, but it's a 2-stage project, so you know you gotta I've talked for a while. Got 2 rockets. Okay, well, thanks for putting all this together, and I guess you know, holler if you got any questions, and otherwise we've got a new launch pad designed to raise the rocket, which I'm hoping that works. You know, it will hopefully raise the rocket with nobody having to help it go up. So, you know, we'll have like a winch on there that actually does the lifting. And
Nice,
so
nice.
you'll
That's
probably
nice.
be the guinea pigs for that, so, but it'll work.
Great. Okay.
Well, just before we, I mean, if we have nothing, just before we leave, I mean, I checked with the velocity of that deployment for the apogee. I get from what I did, I get an angle of like 17.4 degrees and a velocity at apogee of or horizontal velocity of 100 meters per second. So yeah, we can go like 2 degrees more and a bit faster, but we still have only 200-pound force applied on the drogue, so we have
Okay,
a
now is
high safety margin.
Is that 17 degrees at apogee?
No,
Or
17 degrees at
at the igniter?
the ignition of the sustainer.
Okay, so you put enough wind or in there to generate that 17 degrees at that point. Okay.
Yeah, yeah, because the wind has a big effect on the horizontal velocity. So yeah,
Okay. All right.
I think we're safe with the 200-pound force on worst case scenario. We still have like a safety factor of 10 because there's so little air at 45,000 feet that there's not much force.
Okay, but that's force on what though? On the harness?
Yeah,
Okay.
at the bottom
Well,
of the parachute.
that's you know, a fair amount of force. You know, if I was looking at doing you know, like a shock absorber approach, I might you know, Z-fold the harness, and I might say, okay, I got to pull 20 pounds or something like that in order to get that to break. That's quite a bit of force, you know, that you would have to pull on it to generate 20 pounds of force on that. And if you did that a couple of times, now you're dissipating half of the energy of the deployment by doing that. And so you're increasing the safety. So just kind of think about that. You might be able to do a Google search for Tony Alcocer. I don't know if you've ever heard his name, Tony Alcocer, L-O-C-O-C-E-R. And, do Tony Alcocer and shock absorber. And you might find an article that he wrote or a video that he did where he describes that technique.
Not sure I got his name right.
A-L-C-O-C-E-R.
C-E-R, okay. Oh, okay, I got it. Okay.
Yeah, he always posts as T-Fish is his name when he's online. And you might be able to find, he did an article on using shock absorbers on Z-folded harnesses. And you might find that relevant to what you're doing. It's a really, really good thing to do when you're doing out the top deployment so that you dissipate horizontal velocity rather than severing harnesses or shredding drogue chutes.
I'll check him out.
Okay, very good. So be sure to send the video to Andy at the ESRA address, or you'll get a nastygram. And other than that, we'll see you at the competition.
Great.
Thank you.
Thank you.
Okay.
Thanks, guys.
Bye.
Okay.
Je vais l'arrêter avant qu'on finisse. Peux-tu l'arrêter?
That was Jim Jarvis. Il est là, oui.
Le goat.
Je vais peut-être regarder à nouveau des parties de la vidéo.
Elle va-tu spawner quelque part après?